Hello, welcome to 2.8 derivatives and rates of change. In 2.7, we talked about the derivative function f of x at any point a in the domain is, well, we found the derivative of a function f of x at any point a in the domain is the limit as h goes to 0 of f of a plus h minus f of a all over h. So for example, for f of x equals x squared, f prime of a is equal to 2a. Now if you think about it, if we are on the function x squared and we look for the derivative at any point, so if I wanted to know the derivative at 2, the derivative would be 4. If I wanted to know the derivative at -1, the derivative would be -2. And if I go back to -1, the derivative is still -2. There's only one derivative for every input. So the derivative function itself the derivative formula itself is a function. We say that 2x is the derivative function for f of x equals x squared. So pretty much we're just replacing the a with x to identify it more with function notation. So that is for f of x equals x squared, we say the derivative function f prime of x is 2x. So we're doing the same thing as we did in 2.7. We are just changing the a's to x's. So we can identify as a function and just say f of x or f prime of x. So let's find the derivative function for 2x plus x squared. So we're going to do the limit as h goes to 0. So actually I'm going to put in here f prime of x equals the limit as h goes to 0, and now instead of using a's, we're just going to use x's. F of x plus h minus f of x all over h. All right, so now here again, this is where our algebra skills need to be really top-notch. So it's going to be 2 times x plus h, because everywhere we see x, we're going to replace it with x plus h squared minus 2x minus x squared. Actually, I'll do that and put parentheses. All over h. So now let's round this all out. Sorry, I got a little scrunchy there. I thought I had more room. So 2 times x plus h is 2x plus 2h. Then x plus h squared is x squared plus 2xh plus h squared. And then we're going to subtract 2x, and we'll subtract x squared. And that's all over h. Now remember, if you do this correctly, nice things happen. 2x and 2x cancels. X squared and x squared is canceled. All right, looks like everything else doesn't cancel. So I'll pull this up here. So this is going to be the limit as h goes to 0. And I can see that nice things are going to happen. 2h plus 2xh plus h squared all over h. Now remember, in order to cancel this h out, we have to create a factor of h in the numerator. So the limit as h goes to 0 of h times 2 plus 2x plus h all over h. Now we can cross off that h. And the limit as h goes to 0 of 2 plus 2x plus h. Now we're at a point where we can do direct substitution. That's going to be 0. And my final answer is 2 plus 2x. So what did we just do? So therefore, for the function f of x is equal to 2x plus x squared, we found its derivative function to be 2 plus 2x. So the derivative of 2x plus x squared is 2 plus 2x. So if we were to graph this and want to identify the steepness at any point x, we would use the template for the derivative. All right, so here's where things get a little bit crazy. We have alternate notations, sorry. We have alternate notations. So given the function y equals f of x, then we can call the derivative f prime of x. We can also call it y prime. We can also call it dy dx. So this is called Leibniz notation. These are called differentials. And what we can think about is the change in y over the change in x. Remember, like when we found the slope? So that's the change in y over the change in x. If we're looking at it in terms of f, we can write df over dx. We also might see the derivative with respect to x, and then the function being identified. Your book also includes this, Stuart. I never use this notation. I've never seen it outside this textbook, but they do a capital D with f of x, or they do a capital D with the variable with f of x. So I would prefer any of these notations. So for example, for f of x equals the square root of x, we found that f prime of x is 1 over 2 square root of x. We actually found f prime of a was 1 over 2 square root of a, but now we're just replacing the a's with x's to identify it more with the function notation. All right, so here x has to be greater than 0. So therefore, we would say f prime of x equals 1 over 2 square root of x. We could say y prime is 1 over 2 square root of x. We could say dy dx is 1 over 2 square root of x. We could say df dx is 1 over 2 square root of x, right? We could also say the derivative with respect to x of the square root of x is 1 over 2 square root of x. So this, and that guy. So all just different ways to say the same thing. We can even actually do this. The square root of x prime is 1 over 2 square root of x. Right. We say a function is differentiable at a point if the derivative exists at that point. Exists and is finite. So it's a function is differentiable on an interval I if f prime of a exists for all points a in that interval I. I'll call that I right there. So given 2x plus x squared, the domain of this function, well, it's a polynomial, it's all real numbers. The derivative is 2 plus 2x, right? And the derivative is also a polynomial, so its domain is negative infinity to infinity. Therefore, we say f of x is differentiable on negative infinity to infinity. The square root function, well, the domain is 0 to infinity. The domain of the square root function includes 0, but the derivative is 1 over 2 square root of x. Notice this domain, x cannot be in the domain of the derivative. It's 0 to infinity. So functions, the domain of a derivative isn't always equal to the domain of the original function. So therefore, we would say g of x is differentiable on 0 to infinity. The derivative does not exist at 0. All right, let's look at the cube root function. The cube root function, well, the domain is all real numbers. We can take the cube root of anything. Here's the graph of it. The derivative of the cube root function is, and we'll determine how I got this later, it's 1 over 3 times x to the 2/3 power. Now notice the domain here, x now moved down to the denominator. So this isn't, x can't be 0 here. It can be 0 because the cube root of 0 is 0 in the original function. So the domain here is from negative infinity to 0 and 0 to infinity. Therefore, f of x is differentiable everywhere except 0. All right, so what's going on at 0? Imagine if we were walking along this curve right here. What's going on right here? Well, what's going on, if you were taking a hike and you got to this point, you would literally be standing sideways. The tangent right here is vertical. That gets vertical for an instant in time. So this is vertical at x equals 0. And remember, the derivative is the slope of the line tangent to the curve at that point, which is the same as the steepness of the curve at that point. So if the curve is vertical at that point, the tangent line is also vertical, and the slope of a vertical line is undefined. So how can a function fail to be differentiable? Well, a function is not differentiable at a point when it's not continuous, because what we're looking at is how the slopes behave from the left to the right, and the limit has to be the same. So here, this slope is negative, 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 negative all the way to that point. This slope is positive. They never match up. So if a function is not continuous at a point, it's not differentiable at a point. If a function has a vertical tangent, so not continuous, that's the obvious one. Vertical tangent, if it's vertical for an instant in time, then it's not differentiable. That limit f of x plus h minus f of x over h will not exist. Also, if we have a corner or a cusp, a function like this, that would not be differentiable at a point. Absolute value function is also not differentiable because it has a point. The limit would not exist. All right, one more thing. Let's talk about higher order derivatives. We saw for the function f of x equals 2x plus x squared, the derivative is 2 plus 2x. Well, that itself is a function. So let's consider the function g of x. Let's call this its own function, 2 plus 2x. Can you find g prime of x? Well, g prime of x, the derivative of this new function, so forget we even ever had this, the derivative of 2 plus 2x is going to be the limit as h goes to 0 of 2 plus 2 times x plus h, that's g of x plus h, minus g of x all over h. So I didn't write out the template for the difference quotient. G of x plus h minus g of x all over h. All right, now before I go any further and simplify this g of x, do you know what type of function this is? G of x equals 2 plus 2x. If you said it's linear, then you're correct. This is the equation of a line. What is the slope of this line? Yep, it's 2. So the derivative at any point should be 2. This should all just simplify down to 2. So let's see if it does that. Because remember, the derivative is just the steepness of the curve at any point, and this is a linear function, so the steepness is constantly 2. 2 plus 2x plus 2h minus 2 minus 2x all over h. So nice things are happening. We're going to cross off anything that doesn't have an h is going to go away. And we're going to get the limit as h goes to 0 of 2h over h. Those go away. The limit as h goes to 0 of 2. Now remember, the limit of a constant is just the constant. Right. So what we do here is this is the derivative of the derivative. So what we say for f of x equals 2x plus x squared. We found the derivative to be 2 plus 2x, but then the derivative of the derivative was just 2. The notation for the derivative of the derivative is we just use a double prime. So f double prime is just 2. We can even say, get wild and crazy, what do you think f triple prime would be? This is just the graph of the horizontal line too. So the derivative at any point is 0. Yep, there we go. One more problem. Let's find the second derivative for the square root of x. This is going to really test your algebra skills. Ready? right? We already know the first derivative because we've done it a whole bunch of times, right? So for f of x equals the square root of x, we found the derivative function to be 1 over 2 square root of x. So we're going to find the second derivative. We're going to find the limit as h goes to 0 of 1 over 2 square root of x plus h minus 1 over 2 square root of x all over h. So I just found f of x, f prime of x plus h minus f prime of x all over h. All right, so now you ready? Let's put our algebra to the test here. All right, this one's a little bit crazy because we have both radicals and fractions inside of fractions. So the recommended order is to get rid of the fractions inside of the fractions first. So get rid of fractions inside of fractions. I'm going to multiply the top and the bottom by the denominators, the baby denominators. So I'm going to multiply by 2 square root of x plus h. Now, I already have the 2 here, so you can do an additional 2. It's just going to create some more canceling in the end. But because I already have this 2 here, I'm just going to use this. So I'm looking for the least common denominator is actually what I'm doing. So I'm going to multiply the top and the bottom by 2 square root of x plus h times the square root of x, and then do the same thing in the denominator. Now leave the denominator distributed. I'm sorry, don't distribute the denominator, leave it factored. I say that wrong every time. So that times that. 1 over 2 square root of x plus h. Well, the 2 and the square root of the x plus h is going to go away. And all I'm left with here is the square root of x. And when I multiply this times this, the 2 and the square root of x is going to go away. X plus h. Wow, this is getting ugly, huh? H, now leave it like this. 2 square root of x plus h times the square root of x. Right, now notice if we tried to do direct substitution and let h be 0, we would get 0 over 0. So now we're in a position where we have to continue to simplify. And what we're going to do now is we have subtraction that involves a radical. So now I'm going to throw on the conjugate of the numerator. So I'm going to multiply the top and the bottom by the conjugate of the numerator. I know it looks terrible. I promise you I won't make you find the third derivative. The limit as h goes to 0 of product of the first is just x. The inners and the outers cancel. It's going to be minus x plus h. Remember, we're subtracting that whole thing. And then again, leave these. Don't distribute, leave them completely in their factored form. Okay. All right, well, now my nice things are going to start happening. I don't want to write this all over again, so I'm actually just going to do this right here. I'm going to rewrite this numerator as x minus h and cross those off. So save me a lot of writing here. The limit as h goes to 0, and we're going to just have negative h over h, 2 square root of x plus h, square root of x, square root of x plus the square root of x plus h. All right, now these are going to cancel. So close. I know, this is horrendous, but negative 1, 2 over x plus h times the square root of x times the square root of x plus the square root of x plus h. Oops, I got all sloppy with my notation there. All right, now we got rid of that h in the denominator. That's telling me we are at the point of finishing our difference quotient simplification here. So now if h is 0, this becomes 0, and this becomes 0, and what's left is 2 square root of x, square root of x, square root of x, plus the square root of x inside the parentheses, all over negative 1. So close. Ready? Negative 1. 2, the square root of x times the square root of x is just x. So 2x, and the square root of x plus the square root of x is 2 square root of x's. So negative 1, 4x square root of x. Woohoo! So therefore, if f of x equals the square root of x, then its first derivative is 1 over 2 square root of x. And its second derivative would be negative 1 over 4x square root of x. Yes, we did it. Good job. Hanging in there. Whoops, I got a little crooked. Okay. I won't make you find the third derivative, but we could. We could find the fourth derivative. We could do this indefinitely. All right, have fun with these problems. I will see you in chapter 3.